Hello, everyone, and welcome to this homework help video. I plan in this video to give you some assistance with our homework that's not in the textbook. It's the central limit theorem for sample proportions, and you'll find that it's similar to the homework that we were doing in 6.2, the central limit theorem for means. So let me show you this because this does have some additional elements to it. So let me bring up the problem first. And let's just consider the first problem first. It says in a recent survey by a shopping organization, 33% of the 1,000 randomly selected Americans said they were planning on shopping on Black Friday. Suppose that in reality, only 25% actually did shop on Black Friday. Question A, are the conditions necessary to apply the CLT or the central limit theorem satisfied? Explain. Okay, first caveat, first thing to warn you of here is you do need to write this out. You will need to write every time you're testing assumptions, and there are 3. Let me tell you what they are. You can also find this in the slides. So the assumptions behind or underlying the central limit theorem. Okay, so assumptions. Let me do this in black so that it's easier to read. We have assumptions underlying the central limit theorem for sample proportions, okay? The first assumption is, so this is assumption number 1, is that we must have a simple random sample, okay? Every person or every participant in our potential population should have an equal chance of being selected, and they should be selected in such a way that there's no pattern to it. There must be a simple random sample. The second assumption is that the population is at least 10 times as large as the sample that you're taking. So another way to say this is that the sample size can be no more than 1/10 of the population. So you'll see me multiplying by 10 later. This is why. Number 3, this third assumption is that the products of n times p and n times q both must be greater than or equal to 10, okay? And you have to check these mathematically. Now, normally what's going to happen is that this first assumption, it's going to be stated in the problem. You can't approach this any other way. It has to be given to you, but you have to indicate that it's been stated, okay? The second assumption is usually just that, an assumption. You don't know the size from which the population, from which the sample is drawn, but can you safely assume that the population that you're drawing from is at least 10 times larger, that you have 10 times as many people or objects in the population? That's what we want to know. So this assumption, this depends on your good judgment, okay? I have never seen Professor Nick Dell violate this assumption. I have only seen one example of a textbook problem that's ever done it, but this, you still need to go through the analysis of this, okay? Now, this is just straight mathematics. The third assumption, you have to do the math. That's what it boils down to. It's not that hard, but these problems are a little bit time consuming. You need to do the parts. That's the first piece of a problem like this. And then typically we draw the distributions in a little more detail than you're used to, and then we find the probabilities. So this first part is a big deal. And she has every problem where you do this. Sometimes you do this multiple times and you don't even find probability, but we'll get to that. Let me go back to the homework problem so we can look at what's going on here. So it says, are the conditions necessary to apply the CLT satisfied? Well, as I said, the first assumption is it's a simple random sample. And so we have the words randomly selected. That's good enough for us. We can assume that it's a simple random sample. It states that they're randomly selected. So that's met. The second assumption says that the population is at least 10 times bigger than the sample. So let's look at the sample. Our sample is 1,000 people right here. This is our sample, this 1,000 people, right? And they're randomly selected Americans. So we have 1,000 Americans that are shopping on Black Friday. For those of you who might not be familiar with the term, Black Friday is the day after Thanksgiving. It helps companies stay in the black, make profits. That's why it's called Black Friday. So this is the day after a holiday. Now, to answer the second assumption, is it reasonable to assume that the population of all Americans is 10 times greater than 1,000? Well, 10 times 1,000 would be 10,000. So can we safely assume that 10,000 Americans went shopping on? Yes, we can. We can safely assume that that's true, okay? Now, the third assumption requires the math. Now, at this point, I'm going to switch screens here. And I'm going to do some work, okay? So I'm going to do my assumptions here. So for 1A, okay, we have the assumptions. So for the first assumption, there's a few ways that you can write this, but I'm going to say first assumption is that I'm going to say simple random sample is stated. You may see her abbreviate this as SRS when you see it, especially if you're in her class in person. This is common. See SRS, that's simple random sample. Simple random sample stated, that's good enough. The second one is about the size of the population. So we can say that N is 1,000. That was given to us. There were 1,000 people. And the population size, the population of all shoppers on Black Friday in America is greater than 10 times 1,000 people, or 10,000. So this assumption is met. Third assumption, NP and NQ are both greater than or equal to 10. Now, if you had a problem with this part, it was most likely because you weren't sure which percentage you should use. You have a 33 and you have a 25, right? The 33 is theoretical, right? That's what they think. The shopping organization thinks 33% said they were planning on shopping, but only 25% actually did. Use the 25% for that. So here you're going to say this. You're going to say that we're going to write our assumptions. NP is greater than or equal to 10. And NQ is greater than or equal to 10. Now, remember, P is the likelihood that you actually did shop on Black Friday. That's 0.25. And we know from chapter, I believe it was chapter 5. And we also know from chapter 1 about compliments. Either you did or you did not shop on Black Friday. So Q here is 1 minus P. And so this is equal to 1 minus 0.25, which is 0.75. Okay, that's your, so now you do your assumptions, right? So you've got 1,000 people times 0.25. And is that greater than or equal to 10? Well, let's see if it is. If you multiply this out, you'll find that this is 250. And 250 is, in fact, greater than or equal to 10. So 250 is greater than or equal to 10. Now, resist the urge to stop here. You have to choose, you have to test both of these. Okay, so this is a yes on this side. But check this, okay? So this is the same thing. 1,000. We've got 1,000 times 0.75. That should be greater than or equal to 10. This is 750 is greater than or equal to 10. And so this is also yes. And so what we can say is this. We can say that since all of the assumptions are met, excuse me, the central limit theorem can be applied. Okay, that's the first part. Can I do it? Yes, I can. Here's the reason. All right. You can short circuit a little bit of this work, but most of this has to show this second statement. You could shorten a bit, but you have to show these three assumptions. All right, the next part of the problem is asking us to do some graphing, but it's not as bad as you think, okay? So part B says, describe and sketch the sampling distribution of the sample proportion in this situation, okay? So just like we had the central limit theorem for means, we have one for proportions. And what this says is this. Let me go show you on the whiteboard what this is, okay? So it's a normal distribution. So this is describe and sketch the normal or the distribution. It is normal, the distribution of sample proportions, okay? So what we have here is we have a bell curve. As I've drilled into you guys all semester, when you see the word normal, think bell shape. So we're going to draw a bell curve here. Hopefully a better one than I just drew a minute ago. There we go. That looks a little more believable, right? Now, if this is proportions, okay, then we have a mean, but it's the mean of all the proportions. And it turns out that here, I'm going to show you, this has two properties. The mean of the sample proportions, which is what we're trying to locate right now, the mean of the sample proportions, it turns out, is equal to the population mean, P. All right, that's this. Now, the other one is that sigma of P hat, which is our standard error of our sample proportions. Okay, this is our standard deviation or our standard error. Now, this thing turns out to be the square root of P Q over N. PQ over N. Okay, so you do now. Here's another thing about this. So we're going to calculate this in just a minute. But when you calculate this, okay, the first couple problems, especially on your homework, are really, really small values for this. So you can take this out to 6 decimal places or so it doesn't appear to be 0. It's very, very, very small. But when you graph, for graphing purposes only, when you graph on here, you're going to round to 2 decimal places, 2. And the reason for that is that not only are you not going to be able to see any numbers that are that small anyway, but you have to put a bunch of these on the graph, and she doesn't want you writing all those numbers repeatedly. So round it 2 places, okay? So let's do this calculation. Now I'm going to show you something here that I did. Let me go to this, and I'm going to share this for a moment. I'm going to share this here. So I'm going to continue. I'm going to make sure that I'm actually sharing. Yeah, I'm sharing this. Okay. So this is homework that I did some point in the past. So this is the same homework. Now, sig mu of P hat is equal to P, which for this is 0.25. Okay. And P is 0.25. Q, remember, is 1 minus P. So that's 0.75, as we encountered before. if you multiply these two numbers, P and Q, and divide them by the sample size, then take the square root, you get your standard error here. That number for us, 0.0137. Now, you're going to round that to 0.01 for the purposes of graphing it. So, when you come down here, if you'll notice, and I'm going to put this on the whiteboard in a minute, my mean is 0.25. It's right in the middle here. This is my mean of my proportions. This is 0.25 right there. And my standard error is 0.01. So we have 26, 27, and 28. We go 24, 23, and 22. Okay, so this is normal with your mean of 0.25 and your standard deviation of 0.01. That's what she wants for B. Okay, so what we want to do for B is draw our distribution and use two places when used. So this is 0.25 here. This is 0.25. And remember, that came from the problem. And your standard deviation, you just saw me write. I didn't calculate it, but you saw me write it. This is 0.01. I'll do that for you in a minute. So you know what these are. This is 0.22, then 0.23, and 0.24. Just like we would do if we were doing the normal and we had the standard deviation. This is 0.26, 0.27, I should go back a space, and 0.28. Okay, 0.28 right here. That's my describe and sketch. Now, if I wanted to write it, some of you might have seen the notation that looks like this. This is normal. This means normal n, and it's got a mean of 0.25 right here. So put 0.25 in as my mean, and my standard deviation is, I'm going to use the 2 decimal places, 0.01 here. This means it's normal with a mean of 0.25 and a standard deviation of 0.01. But this picture is sufficient with these calculations here. If you say, well, I know that my mean here is 0.25 because that's given to me. This is 0.25. And this, remember, this one came from the fact that you had the square root of this is 0.25. This is the complement of 0.25, which is 0.75. And I divided it by 1,000 and took the square root. So that's how that's done with part B. Okay. Let me show you here. Open up the calculator. And let me show you the calculation here. So this is second square root. We do open parenthesis 0.25 times 0.75 close. Then we go divide it by, and we put, oops, except I need to make sure that I'm under the radical when I do that. So divided by 1,000. And I need to get rid of this extra division sign. Make sure you're under the radical, the whole piece of it. Make sure that the numerator is in parentheses. So 0.01369. So that 36 turns into 7. Okay. Now we're going to actually start finding probabilities, but in this section only. Okay. You do not have to convert your probabilities to z-scores. Okay. It is possible to use second distribution, normal CDF, without converting to the z-score. And that's what we're going to do in this particular section. Okay. Just trying to save you some work. So let's go back to our problem that we're doing. And let's look at what she wants us to do. I'm going to go back to the homework here. And it says, what is the probability? This is part C. What is the probability of selecting a random sample of 1,000 people and getting 33% or more saying that they shopped on Black Friday? 33% or more. All right, so what we're going to do is, I'm going to go back to our whiteboard for a minute, and I'm going to, now that I've done part B, okay, I'm going to label part C on my graph. Okay, I'm going to use, let's use blue for that. Okay, so I have 0.25 in the middle. I want 0.33. Now, keep in mind that 0.33, if I only go 3 standard deviations, is not on here. Okay, but I can make an assumption that it's way out here somewhere, right? Because this is 100th, 200ths, 300ths. I've still got 5 more hundredths to go, all right? So this is going to take a minute to get me there, all right? So I've got to be out at this answer somewhere here, okay? This answer here, let me undo that squiggle. This part here, let's say this is 0.33 all the way out here. Now, I know that's not to scale and I know that's not realistic, but let's just say, for the sake of example, that it is. Okay. What we're looking at is we're looking at this here. Okay, we're looking at how likely is it that we're in here. We're more than 33%. Now, your z-score for this is going to involve this, but we're not going to convert to a z-score. You can, and she has one slide where she does that for you, but she doesn't require it. What you're going to do is you're going to go to the distribution screen. So what you need are these two numbers here. You need 0.25, the mean, and you need the long decimal version, not the huge decimal version, but you need at least the 4 decimal place version of this answer. So what we need here is we need 0.01, whoops, 0136, okay? This is what we need for our calculation. So let me show you how that works. So here we go with bigger than 33. So what we're going to do is our lower is going to be 0.33, our proportion. Our upper is going to be infinity. Second infinity, 99. Okay. Now, our mean is going to be what our proportion was for the population. So that's 0.25. And as I've said, the sigma is our 4 decimal. So 0.0137. And if I paste that in, I get, now, this is one of those cases where we get a small answer, 2.6927, whatever, and to the negative 9th power. This means that this decimal point moves 9 places to the left, this way, the way you see my arrow going, okay? Here's my arrow. See, here's my arrow. It's going this way, going to the right. So, or to the left, I should say, to the left. So if I go to the left 9 places, what this means is that I have something that looks like this. Let me go and show you. Now, here's my decimal point, right? It's going to go this way, but it's going to go 9 places this way. Okay, so we have point and then 8 zeros and then a 262. Okay, so we end up with something like 0.0000678 and then 262, so a 3 there. That would be my answer if I rounded. Okay, and so that's so close to 0 that it's not very probable. Okay, but that's what's going on there. Okay, that's part C. So here I'm going to go to part C and I'm going to say, you can write this. You can write the probability of, this is part C, probability of P hat larger than 33%. Larger than 33 is going to be, and then remember that's a decimal, okay? That's going to be point, this is 0. And if you remember, 1, 2, 3, 4, 5, 6, 7, 8, and then a 3. So that was our probability, okay? We're gonna do one more probability in this problem. And then I'm going to close this video and come back hopefully with problem number 2 in a little while. But I'm gonna do part D for you right now. So here, part D says, what is the probability that at most 190 of these 1,000 people shop on Black Friday? What is the probability that at most 190 of these people? Okay, So here, what they've done is instead of giving you a percentage, like we normally do, we normally give you a percentage. What we've done is we've given you a number of shoppers, okay? So we want, the way that we would write this, if we would say this, the probability of, my apologies, folks, I had a brief Zoom interlude there. But what we're doing is we're doing part D of number 1 here. So what I'm going to do is open up the screen one more time and share my screen with you. And we're going to say that what is the probability that at most 190 of these people shop on Black Friday? Well, if I share the whiteboard and I say, well, okay, my probability is X. This time it's X. This is not a proportion. This is a number of people. X greater than, it's at least, or sorry, at most. Let me check. I believe it says at most. So let me check this. What is the, yeah, at most. So 190 is the most. So let me go back, and because I almost made a very common mistake. 190 is the most. So what I'm going to do here is this is less than or equal to, because 190 is the maximum, right? Before I can find my probability, I need to know what proportion this is. So I'm going to calculate p hat. And p hat, which is my sample proportion, is the number of people that fit the characteristic. In this case, X, which is 190. There's 190 people, and there's 1,000 people total in the sample. So what I'm going to do here is I'm going to write 190 over 1,000, okay? And that proportion is 0.190, okay? This is my proportion. So when I go to calculate this, just to give you some perspective, I'm not going to draw the whole distribution from from letter B, but here's my mean is 0.25 right here. And my proportion that I'm looking at is 0.19. So it's somewhere over here, right? It's way over here somewhere. And this is 0.19. I want my area that is at most this. So in this case, I want this. I want this area, okay? And remember that on this side, this is negative infinity, okay? So what I'm going to do is I'm going to say this. I'm going to get my calculator and I'm going to say that I want second distribution, inverse norm, which is, I'm sorry, not inverse norm, normal CDF, normal CDF. My lower is negative infinity. So I'm going to go negative, second E99, and I'm going to go to upper, which in this case is going to be 0.190. 190. Okay. My mean is still 0.25. My sigma is 0.0137. I'm going to paste it in, and I'm going to get this tiny, tiny number. Once again, 5.95 times 10 to the negative 6. What I've done here, what this is this with 6 decimal places to the left. So what I'm going to do is move this way, 6 places. Remember that moving the decimal over the 5 counts as 1. So here I have 1, sorry, this is 0, this is, let me select the mouse. This is, here I have 1, 2, 3, 4, 5, and then 6. Now, why is it 6? Because this is 5, 9. So this, this marking, I went 6 places, so I have 5 zeros, notice, okay? And I have a 6 at the end. That is how I'm getting the probability. And again, it's very, very, very small. Not all the time is it quite this small, but this is what we're after. And I hope that that has helped you some with the first problem of the homework. Hopefully I'll be back with additional problems from the homework, but I'll see you soon in my next video, everyone. Hope you're doing well, and I'll see you next time. Bye for now.